Hello friends, welcome back to my new video. Today we will learn very basic and fundamental things, that is rate and rate constant in pharmacokinetics. So it's a very basic things, but most important we should have fundamental on it. So today I thought I'll discuss on rate and rate constant. Let's start. So in this contest we'll going to discuss about introduction to the rate and rate constant, then zero order kinetics, then zero order half-life, then first order kinetic, and about first order half-life. So let's start. So first come to what is a rate and what is rate constant. So rate of reaction is nothing but the velocity with which a reaction or a process occurs is called as a rate, and how the concentration of the drug or reactant influence the rate of reaction or process is called as order of reaction or order of process. So any process, so here we have the importance of discussing about different pharmacokinetic process. So in pharmacy also we can discuss different process like degradation process or any other process we can take into account, and same zero order process and first order process can be taken into account. So here our importance is to discuss about various pharmacokinetic process. So let's start. A common equation is there to describe the different rate process. If the concentration of the drug is denoted as C at the time 0, the initial concentration is C0, and the time t the concentration is Ct. The rate of change of drug concentration, that is dC by dt, is equal to minus k C to the power n, where k is rate constant, n is order of reaction, and unit of dC by dt is nothing but micro mcg, that is microgram per ml per hour. So that is dC by or unit of dC by dt or rate of reaction. Then come to zero order kinetic, which is otherwise called as constant rate process. So dC by dt is equal to minus k C to the power n, where n is equal to 0, dC by dt is equal to minus k0 C to the power 0, or you can say C to the power 0 is 0, and so finally the equation is dC by dt minus k0. K0 is zero order rate constant. A zero order process can be defined as one whose rate is independent of the concentration of the drug undergoing the reaction. That is, the rate of reaction cannot be increased further by increasing the concentration of the reactant. You can notice from this equation dC by dt is equal to minus k0. There is no concentration term. So from this equation we can define this process, that is zero order process, as independent of the concentration. So the rate is independent of the concentration. So there is the rate of reaction cannot be increased further by increasing the concentration of the reaction. Even if the concentration of the reactant increases, so there will be no change in the order of reaction. So that is the most important aspect in the zero order kinetic. So that you have to remember. So after simplifying this equation, dC by dt is equal to minus k0, then dC is equal to k0 dt, that is a simple mathematics, cross multiplication. Then integrating both the sides from t is equal to 0 to t, that is C minus C0 is equal to k0 t, that is the equation after integration. So final equation is C is equal to C0 minus k0 t. So after integration and simplification, you will get the final equation like C is equal to C0 minus k0 t. So you have to just learn about the simple integration process. Then after you can do from derivative to integration, how it is calculated. Simple formula you have to remember, where k0 is equal to zero order rate constant, that is in microgram per mg per minute. So then come to zero order kinetic, that is a constant process, as you know already we discussed. And this zero order graph can be plotted by plotting the graph between dc by dt and dc by dt versus time and concentration versus time. When you are plotting a graph between dc by dt versus time, you just notice that there is a steady state, means there is no change in the rate process. That is a steady state, constant, parallel to the x-axis or time axis. When you will plot a graph between plasma drug concentration and time, so there will be a constant decline in the initial drug concentration. That is C0 is constantly declining, and when and it is linear, it is following linear kinetic when you are plotting a graph between C versus time. And if you want to calculate that C is equal to C0 minus K0 T, that is in the form of Y is equal to mx plus C. So that is nothing but a equation of straight line. And from this graph you can notice that constant decline is there is a constant decline and it is indicating a linearity. Okay, linear graph is there. And negative sign indicates there is a constant decrease in the plasma drug concentration with respect to time from initial to the final. So if you want to discuss about this application of this zero order kinetic in our pharmacokinetic process, so the example is constant rate IV infusion. So that is following zero order kinetic, then metabolism or protein binding above the saturation point. Once the saturation point is reached, so after that, even if you increasing the concentration of drug, there will be no metabolism or protein binding. So after the saturation point, so that will follow zero order kinetic. So up to that saturation point, it will follow first order kinetic. Then drug release from ideal control release formulation. So any control release formulation will release the drug in a zero order rate. So that is the most important application of this zero order kinetic in the drug delivery system. Then come to zero order half-life. So half-life is nothing, T half is indicated in the T half. So half-life is defined as the time required for the concentration of the drug to reduce by 1/2. Means whatever the initial concentration is there, that concentration, the time taken to reduce the initial concentration to half, that is called as half-life. So when T is equal to T half, at that time final concentration C is equal to C0 by 2. And the zero order equation become, just you recollect, in place of C you are writing C0 by 2, and in place of time T you are writing T half. Okay. So the after simplification, simple mathematics, so simplification, you will get the final equation T half is equal to C0 by 2 K0, or you can say half, instead of half you can write 0.5 C0 by K0. So equation for half-life shows that the T half of zero order process is not constant but proportional to the initial concentration of the drug C0 and inversely proportional to the zero order rate constant K0. So T half is directly proportional to C0 and inversely proportional to K0, that is constant. So this is about zero order kinetic. Next come to first order kinetic, or it is called as linear kinetic. Zero order kinetic was called as constant rate kinetic and first order rate kinetic is called as linear kinetic. So the equation, come to the common equation, dc by dt is equal to minus k c to the power n. When n is equal to 1, dc by dt is equal to minus k1 c. The first order process is the one whose rate is directly proportional to the concentration of the drug undergoing reaction. That is, greater the concentration, faster the reaction. Means it is directly proportional. If you are increasing the concentration, rate of process or rate of reaction or rate of the process will increase constantly. Means it will increase, directly proportional. Then dc by dt is equal to minus k1 dt. Okay, by integrating both the sides and converting them into natural logarithmic form, the equation will be ln c minus ln c0 is equal to minus k1 t. So k1 stands for first order constant, or first order rate constant. T, that is time. C0 is the initial drug concentration. C is concentration of the drug at the time t. So after this natural logarithm form, if you convert to the exponential form, then the equation will be c is equal to c0 e to the power minus kt. So that is a exponential equation. Or converting to the log form, log base 10 form. So when you are converting to log base 10 form from the natural logarithm, so it will be ln is equal to 2.303 log. So by replacing this value, then the final equation in the log form will be log c is equal to log c0 minus kt divided by 2.303. So this is the final equation for the first order kinetic. Again, I can say you, just use c. It is in the form of y is equal to mx plus c. So in this equation, what is y? Y is nothing but log c. X, what is x? X is nothing but time. So when you are plotting a graph between y, that is log c, versus x, that is time, then you will get a linear curve having slope. What will be the slope? Minus k divided by 2.303. That will be the slope, and y-intercept will be log c0. So this is in the form of linear equation, and negative sign indicates there is a constant decrease in the plasma drug concentration level with respect to time. So next come to graphical representation. When you are plotting a graph between percentage of C, percentage of plasma drug concentration versus time, so there will be a Cartesian plot. Okay, curvature will be there. Curve in the plasma drug concentration decrease in a curve way, not in the straight line or linear way. But when you are plotting a graph between log C versus time, already I told you that equation in the form of y is equal to mx plus c, or in the form of linear curve. So when you are plotting the graph between log c versus time, you will get a straight line, and there will be a constant decline in the plasma drug concentration. So, and slope having minus k divided by 2.303, or you can say 0.434 k, and there will be y-intercept, that is log c0. And if you take the example of this pharmacokinetic process with respect to first order kinetic, so most pharmacokinetic process like absorption, distribution and elimination follow first order kinetic. Then we come to the first order half-life. If you substitute the value of C0 by with respect to C0 by 2 at the time t half, and t half is the first order equation, and solve, then you will get the equation like t half is equal to 0.693 divided by k. So my dear friends or students, only in this case you require certain mathematical knowledge how to convert that equation log c is equal to log c0 minus k t divided by 2.303 to t half form. Means in place of time you have to write t half, in place of c you have to write c0 by 2, and after simplification simply you will get this equation t half is equal to 0.693 by k. So this is most important. Just you see that this is based upon your fundamental difference between zero order and first order kinetic. So how you will compare and differentiate between this zero order and first order kinetic? First one is equation. Come to the equation. So zero order equation is minus dc by dt, general equation dc by dt is equal to k0, and first order equation is minus dc by dt kc. So in zero order kinetic, the rate process is independent of concentration of the drug, whereas in first order kinetic the rate process is directly proportional to the concentration. And final equation, come to the final equation, zero order is equal to C is equal to minus K0 T plus C0, where in first order reaction C is equal to C0 e to the power minus KT. Rate constant unit, so microgram per ml per hour, and in case of first order reaction 1 by hour. Half life T half unit is time, but half life equation is 0.5 C divided by K0, and T half for the first order is 0.693 by K, which is a constant, but in case of zero order it is not a constant. Effect of time on rate, zero order rate is constant with respect to time. First order rate will change with respect to time. As the concentration changes, the rate first order rate will change. Then effect of time on the rate constant. Rate constant will respect to time changes as the concentration changes. Rate constant remain constant with respect to time. So both you should see. First one is what is the effect of time on the rate, and effect of time on the rate constant. Two are two different things. One is what is the effect of time on the rate, and what is the effect of time on the rate constant. So effect of time on the rate in case of zero order is constant. In case of first order it will change with respect to time. Then in case of rate constant, so rate constant with for the zero order, the rate constant with respect to time changes as the concentration changes, but in case of first order the rate constant will remain constant with respect to time. Then another thing, draw concentration versus time plotted in the rectangular coordinate. If you plot draw concentration versus time in the rectangular coordinate for the zero order, it will decline linearly for the zero order rate process, whereas the draw concentration decline non-linearly for the first order rate process. Again, draw concentration versus time plotted on the semi-logarithm plot graph. Draw concentration decline non-linearly for a zero order rate process, and draw concentration decline linearly for a single first order process. So these are the basic difference between this zero order and first order kinetic. And in when you are studying biopharmaceutics and pharmacokinetic, you will come across various applications of zero order and first order throughout your calculation of different pharmacokinetic parameters in case of compartment studies. So you should have this fundamental knowledge: what is zero order, what is first order, what is how the graph is plotted between, and how the graph is behaving. So everything depends upon your fundamental things. So I think you will learn some fundamental basics from this video, and you'll see next time with another video and fundamental things. Till then, bye bye, take care of yours.